Okay, an alternate way to graph a cosecant curve is we can graph the associated sine curve. So by associated sine curve, we mean we're just going to change cosecant to sine. And then we can graph this however you want. We can use the a sine omega x plus phi plus b form of a sinusoid. And then we can read off a is 2, so omega is 3, b is 0, and b is 1. So this tells us that the amplitude of this sine curve is the absolute value of a, which is the absolute value of 2, which is 2. This gives the period is 2 pi over omega, which is 2 pi over 3. The phase shift is negative phi over omega, which is 0. And the vertical shift or baseline is y equals 1. So we start at the phase shift 0, and we go out to the period 2 pi over 3. We average these to get the middle quarter mark. So we add them together and divide by 2. That's going to give us pi over 3. We add these together and divide by 2. We get 3 pi over 6, which is pi over 2. I add these two together and divide by 2. I get pi over 6. The next thing is I look at the baseline, y equals 1. I'm going to dot that in, like so. And the amplitude, A is positive, which means we're going to start moving upwards 2 units away from the baseline. So here's y equals 1. So I'm going to start at 0 up at the baseline. A is positive, so I move 2 units up. So up to 3. Then back to the baseline. Then down to negative 1 at pi over 2. So once again, I'll move this label out of the way. Then back to the baseline. And this would be my sine curve. Okay? So to get the cosecant curve, I would just have to remember that the baseline here corresponds to the original y-axis, so those are the original zeros of the sine curve. So on the cosecant curve, you're trying to take the reciprocal of those zeros, and that's going to cause the vertical asymptotes. So the vertical asymptotes are going to happen when you cross the baseline. And then these points are going to stay those points. And then I imagine I'm taking reciprocal values to get my branches of the cosecant curve this way. Okay, so where this is increasing and then decreasing, the cosecant curve is decreasing, then increasing, and then vice versa. Okay, so once again, an alternate method to produce the same graph. So that'll do it for number 2. All right, last but not least, we're asked to graph one cycle of this tangent curve. So I go back to the standard tangent function, and it gets graphed over the interval minus pi over 2 to pi over 2. And so the quarter marks here are 0, minus pi over 4, and pi over 4. So I can look at what's inside the tangent, the argument of the tangent, and set that equal to each of these old quarter marks to get the new x's. So I'd set pi over 2 minus x equal to negative pi over 2. Pi over 2 minus x equal negative pi over 4. Pi over 2 minus x equal to 0. Pi over 2 minus x equal pi over 4. Pi over 2 minus x equal pi over 2. And so the way I would solve each of these equations is I would subtract pi over 2 from both sides, which would then shift it to the left pi over 2 units. Then I would divide by negative 1, which would follow that up with then a reflection about the y-axis. So when I solve this, I get here x equals pi. When I solve it here, I get x equals 3 pi over 4. Here I get x equal pi over 2. Here I get x equal pi over 4. And here I get x equals 0. So notice the new quarter marks are decreasing. That corresponds to running the function backwards. That's because of the reflection. Now, of course, it's time to get the new y's. And we get the new y's same as before. We plug in the new x's. So for x equals pi, y is the tangent of pi over 2 minus pi, which is the tangent of negative pi over 2. This is undefined, which means we're getting a asymptote there. For x equals 3 pi over 4, I get y equal tangent pi over 2 minus 3 pi over 4, which is tangent of negative pi over 4, which is negative 1. For x equal pi over 2, I get y equal the tangent of pi over 2 minus pi over 2. That's the tangent of 0, which is 0. For x equals pi over 4, I get y equals tangent pi over 2 minus pi over 4, which is the tangent of pi over 4, which is 1. And finally, for x equals 0, I get y equal tangent pi over 2 minus 0, which is the tangent of pi over 2, which once again is undefined. And so as before, you notice when you substitute in the new x's, the argument of the tangent is always going to give you the original quarter marks. All right, so now it's time to put all that information to good work, or to good use. The new x's we got were pi, 3 pi over 4, pi over 2, pi over 4, and then 0. And when we plugged those in, we plugged in pi, we got a vertical asymptote. When we plugged in the 3 pi over 4, we got the negative 1. So I'll move that down there. At pi over 2, we got 0. At pi over 4, we got 1. And at 0, we got another vertical asymptote. Now I connect the dots in the pleasing tangent-like fashion. So it comes down and heads over and heads down. That's not a very pleasing tangent fashion. It's because my y scale is skewed, so it's getting more stretched out than it should be. The tangent and cotangent curves should look something like that. I can organize it right here. Something like that. That's as good as I'm going to get it here on the tablet. Now, you may look at this and say, wow, this matches the fundamental period and the shape of the cotangent function, And so just as a little side note here, thanks to the cofunction identity, the tangent of pi over 2 minus x is in fact the cotangent of x. So graphing this function should match up with the cotangent, and it just so happens that the fundamental period of the tangent through this transformation matches up with the fundamental period of the cotangent. That'll do it for checkpoint quiz 10.5.